Last time on Galaxy Megabuilds, we tried to build a tunnel across the Atlantic Ocean, 54 minutes from New York to London at Mach 6.5, $20 trillion, the kind of ambition that makes civil engineers weep into their coffee. Today, we're doing something arguably more insane. To my Des, the chef extraordinaire, I know you're cooking amazing food, and I'm cooking this special shout out to you. Thanks for being you. Picture this, the Daytona 500, 40 stock cars, 200 miles per hour. Pack racing so tight you could pass a credit card between bumpers. Now take all of that, the speed, the noise, the barely controlled chaos, and suspend it 700 feet above open water on a Golden Gate Bridge-style suspension bridge. Bridge-tona, Art Deco towers rising like concrete cathedrals, 31-degree bank turns sweeping over the bay, fog rolling beneath the cars like a blanket. Stock cars threading through tower legs at racing speed, their exhaust echoing off steel cables thick as tree trunks. The most spectacular motorsport venue ever conceived. Imagine the broadcast shot, helicopter tracking a pack of cars through turn 2, the bridge deck curving away into morning mist, nothing but ocean underneath. Imagine tailgating on a bridge deck with a view that makes the Golden Gate look like a parking lot. It would be magnificent. It would be the 8th wonder of the world, and it is physically impossible, not impractical, not expensive, impossible. Let me show you why. Daytona's 31-degree banking isn't a suggestion, it's physics. Without that slope, centrifugal force at 200 miles per hour would slingshot cars off the track like a catapult. So you need that banking. And on the high side of that banking, you need windscreens. Solid walls to keep crosswinds from flipping a stock car into the grandstands. Here's the problem. Suspension bridges survive by letting wind pass through them. That's not a feature. That's the entire survival strategy. The Golden Gate Bridge uses an open steel truss deck specifically designed to let wind flow around and through the structure. Air moves through the gaps, pressure equalizes, the bridge stays stable. It's elegant, it works. Engineers spent 80 years perfecting it after the Tacoma Narrows Bridge, Galloping Gertie, twisted itself apart in 40-mile-per-hour winds in 1940 because the solid deck caught air like a wing. Now, we want to bolt giant windscreens, essentially solid walls, to a suspension bridge deck. You've just turned the bridge into a sail. Wind profile increases catastrophically. The deck catches crosswinds, generates lift, starts oscillating. At racing speeds, those windscreens aren't protecting the cars, they're destroying the bridge. The structure that needs to breathe is now choking on its own aerodynamics. The bridge fights the physics of the ocean, and the ocean always wins. Suspension bridges move. They are designed to move. Temperature changes cause the deck to expand and contract by feet, not inches. The Golden Gate Bridge shifts over 5 feet seasonally. Steel makes up 45% of bridge material, and steel has a massive thermal expansion coefficient. Summer heat, the deck stretches. Winter cold, it contracts. Bridges handle this with cone-shaped steel expansion joints, interlocking teeth that slide past each other as the deck breathes. You've driven over them. That rhythmic thump, thump, thump on highway bridges, that's expansion joints doing their job. Formula 1 racetrack tolerance, 1/8 inch, 3.22 millimeters. Highway bridge expansion joints, 13 millimeters of vertical deflection. A stock car hitting an expansion joint gap at 200 miles per hour isn't a bump. It's a launch ramp. Current asphalt technology cannot stretch several feet without catastrophic cracking. The bridge needs to breathe. The racetrack needs to be seamless. Those two requirements are fundamentally incompatible. You can build a bridge that moves, or you can build a racetrack that's smooth. You cannot build both in the same structure. Daytona's 31-degree bank turns are massive earthen embankments, 50 plus feet of compacted marl clay sitting on bedrock, holding millions of tons of weight through pure mass. On a bridge, you'd build that banking as a hollow steel truss wedge, triangulated space frame sitting on top of the main deck, steel deck plate topped with asphalt, lighter than concrete, but still, you're adding hundreds of tons of dead load per segment. Then you need safer barriers, steel and foam energy reduction barriers, the technology that saved countless NASCAR drivers' lives. Those require reinforced concrete retaining walls, miles of them, more dead load. Now, here's where the engineering loop collapses. More dead load means you need thicker cables. Thicker cables mean heavier towers. Heavier towers mean deeper foundations. Deeper foundations in open water mean exponentially higher costs and reduced allowable span length. Shorter spans mean more piers in deep water. More piers mean more foundations. More foundations mean more cost. More cost means You see where this goes, and here's the structural nightmare. The cables on the high side of the banking would be shorter than the cables on the low side. Asymmetric loading. The deck wants to twist, the tower wants to lean. The entire structural logic of a suspension bridge, symmetry, balance, distributed load, breaks down the moment you ask it to be a racetrack. Bridge-tona, rejected, unstable, windy, flexible, unsafe. Lake Michigan. Hypertube, validated, controlled, rigid, dry, fast. It requires the budget of a small country and the cooling system of a nuclear power plant. But the physics hold. Every piece of technology exists. This is not science fiction. This is science waiting for the check to clear. Cost reality. Estimated $500 billion for the deep speedway. The Channel Tunnel cost $6 billion, adjusted for inflation. Our transatlantic tunnel concept was $20 trillion, viable only with a dual use case. High-speed freight and transit, not just racing. A stepping stone to the global transatlantic vision we explored last time. The dream funds the reality. But here at Galaxy Megabuilds, we don't stop at the problem. We find the pivot. Bridge-tona is dead, but the idea, a NASCAR superspeedway built with extreme engineering, that idea is just getting started. Remember the Transatlantic Tunnel episode? The one where we tried to connect New York to London with a neutrally buoyant tube suspended below the ocean surface? That technology, immersed tube tunnel construction, gives us the answer. Here's the insight. A submerged tunnel bypasses every single problem the bridge had. No wind, no sail problem, no aerodynamic instability, no Tacoma Narrows failure mode, no thermal expansion joints. The underwater environment is thermally stable, constant temperature year-round. The tunnel doesn't expand and contract like a bridge deck baking in the sun. The racing surface stays seamless. No dead load limits. The lake bed carries the weight. You're not asking cables to hold up millions of tons of banking and barriers. You're resting a concrete box on sand and rock. Compression, not tension. The oldest, most reliable structural principle in engineering. The bridge was chaos. Flutter, flex, shear, thermal expansion, wind loading, asymmetric cables. The tunnel is control. Laminar flow, constant pressure, zero deflection. Rigid structure. The bridge fights the physics of the ocean. The tunnel bypasses them. So here's the new venue, Lake Michigan, an inland sea. Maximum depth, 923 feet. Target depth for our tunnel, 100 feet below the surface. That's a thermal stability zone. Constant temperature, minimal wave action, zero surface weather interference. Fresh water. No saltwater corrosion eating away at concrete and steel. No chloride ions causing spalling. Surface conditions can mimic the North Atlantic in a winter storm, but underwater, calm, predictable, engineerable. Welcome to the Lake Michigan Hypertube, a 2.5-mile tri-oval NASCAR superspeedway. 100 feet underwater, permanently dry, permanently lit, permanently fast. If you're a NASCAR fan, what I'm about to describe is going to sound insane. But every piece of technology I'm about to reference exists. It's been built. It's been proven. This isn't science fiction. This is science, waiting for the check to clear. Immersed Tube Tunnel technology, not theoretical. Currently in use at the Hong Kong-Zhuhai-Macau Bridge, the longest sea crossing on Earth. The Chesapeake Bay Bridge Tunnel, the Fehmarn Belt Fixed Link, currently under construction in Europe using 73,000-ton precast elements. Here's how you build an underwater racetrack. Step 1. Build the tunnel somewhere else. You don't build this underwater. You build it in a dry dock on the Lake Michigan shore. Wisconsin shipyards, massive prefabricated rectangular concrete boxes, not circular. Tunnel boring machines give you circles. We need a flat, wide surface for racing. Horrendous. Width of 8 highway lanes, 600 to 650 foot segments. Each one is a self-contained module. Factory level quality control before it ever touches water. Step 2, turn concrete into a boat, seal the segments. They're hollow. They float via buoyancy. Tow them with GPS guided tugboats over a pre-dredged trench in the lake bed. Step 3, sink them. Flood the ballast chambers. The segment descends into the trench. Divers and remotely operated vehicles guide it into position. Sandflow bedding underneath for even load distribution. Step 4, the seal. This is where it gets beautiful. Between each segment, Gina gaskets, thick rubber seals. As the segment settles into place, hydrostatic pressure, the weight of the water above, crushes the gasket into a compression seal. The deeper the water, the tighter the seal. The force that wants to destroy the tunnel is the same force that makes it watertight. The enemy becomes the architect. Backfill the trench with angular locking fill and heavy rock armor. Within months, the tunnel looks like it's been there for centuries. Real-world construction durations for Immersed Tube Tunnel projects. Lefortovo Tunnel in Moscow, 3.3 years. Madrid Southern Bypass, 4.4 years. Tokyo Bay Aqualine, 8.9 years. This is proven methodology. We're just applying it to motorsport. Inside the rectangular concrete box, echelon paving, 3 or more asphalt pavers working side by side, laying asphalt simultaneously. No cold joints, no seams, one continuous pour. Polymer modified asphalt with styrene butadiene styrene for flexibility. Georgia granite or Florida lime rock aggregates for grip. The same stuff Daytona uses. Wearing course over 1-year course with precast concrete roads, rigid base, Formula One seat, NASCAR top, and here's the magic. Constant underwater temperature eliminates thermal expansion cracking. The surface doesn't expand and contract. It doesn't bake in the summer sun or freeze in winter storms. For NASCAR fans, imagine a track surface that never develops bumps, never needs repaving because of weather damage. The racing surface is perfect every single lap, every single race. 31-degree turns, built as a steel truss framework wedge sitting on the flat tunnel floor. A ramp inside a box. The banking transfers dynamic loads. The centrifugal forces of 40 cars cornering at 200 miles per hour, down through the steel framework, into the tunnel floor, and out through the concrete walls into the lake bed. Steel deck plate topped with asphalt. The same banking geometry as Daytona, the same physics, but the banking exists entirely inside the tunnel. No wind, no weather, no expansion joints. Every problem that killed Bridge-tona doesn't exist down here. The Channel Tunnel. The channel connecting England and France uses 480 kilometers of cooling pipes for electric trains. We're running 40 V8 combustion engines at 750 horsepower each, 30,000 combined horsepower generating heat in a sealed concrete box. Solution. Lake Michigan is the cooling plant. Pump surrounding lake water through cooling pipes embedded in the ceiling and walls. 4.2 trillion gallons of fresh water as the heat sink. The temperature differential from a 3-hour race is negligible. The lake absorbs the heat. The tunnel stays cool. The engines stay happy. 40 cars pushing air at 200 miles per hour in a sealed tube creates a pressure wave, a high-speed air slug. Fix, piston relief ducts, channel tunnel design. Large vents connecting the main tunnel to a parallel service tunnel, equalizing pressure before it becomes a problem. Ceiling-mounted, longitudinal jet fans push air in a controlled circuit. Exhaust gets moved. Fresh air gets cycled in. There will be a slight haze, a mist from humidity and heat management. It'll be dank, industrial, almost cyberpunk, a concrete cathedral of speed. Permanent twilight lighting from continuous LED stadium light strips mounted on the ceiling corners. No shadows, no glare, no rain delays. The track is permanently dry. Precipitation, 0%. Humidity, controlled. Track temperature, constant. For NASCAR fans, imagine never losing a race to weather. No more sitting in the grandstands watching jet dryers circle the track for 2 hours. No more Monday makeup races. No more rain-shortened finishes. The racing surface is perfect every single lap, every single race. If this is expanding your world right now, if you're seeing motorsport infrastructure in a way you've never seen it before, hit subscribe. Hit the notification bell, because we're just getting started. The outer tunnel wall gets lined with safer barriers, steel and foam energy reduction barriers, steel tubes backed by polystyrene foam. The same technology used at every NASCAR oval in America, retrofitted onto a concrete tunnel wall. Inner side, concrete pit wall. A stock car hits the wall at 160, the foam compresses, the steel flexes, the driver walks away. Same physics, same safety, just underground, modeled directly on the Channel Tunnel. 3 parallel tubes. Race tube A, central service tunnel, race tube B. The service tunnel is kept at higher pressure than the race tubes. Positive pressure, differential. Smoke physically cannot enter. If there's a fire in the race tube, smoke gets pushed away from the escape route. Cross passages every 375 meters for immediate driver rescue. Compartmentalization, blast doors seal off breach sections. Inert gas suppression systems for electrical fires. Doesn't damage equipment. Doesn't harm people. Just starves the fire of oxygen. Emergency egress slides for rapid vertical evacuation. No open infield. Pit road runs along the flat section, parallel to the straightaway. Pit crews operate in enclosed pit boxes, backing up to the service corridor. Heavy steel cross-passage doors every 375 meters connect pit lane to pressurized safety zones. It's claustrophobic, it's intense, it's the most controlled pit environment in motorsport history. For NASCAR fans, imagine your pit crew working in a climate-controlled underground facility instead of 95-degree July Florida heat. Imagine pit stops where the air wrench never overheats, where the jack doesn't slip on rain-slick pavement because there is no rain. Pit stops under 12 seconds every single time. The tunnel isn't just concrete and steel, it's a living structure. Carbon fiber composite outer shell for strength to weight ratio. Managed buoyancy, self-healing concrete with biocalcification agents. Microscopic bacteria embedded in the concrete that activate when water seeps in, producing limestone to automatically seal microcracks. Fiber brag, grating sensors embedded in the walls, a nervous system of fiber optics detecting strain, temperature, and leaks in real time. The tunnel feels where it hurts before the damage becomes visible. At depth, humans can efficiently maintain infrastructure. ROV fleets, remotely operated vehicles adapted from offshore oil technology. Inspect anchor cables and joints externally. Internal autonomous drones scan for structural fatigue and seal integrity. The tunnel maintains itself. Lake Michigan is one of the largest freshwater ecosystems on the planet. So let's address this honestly. Immersed tube tunnel construction is one of the least invasive underwater construction techniques. Trench dredged, tunnel placed, trench backfilled, the rock armor becomes habitat. Freshwater mussels colonize it, crayfish move in, lake trout use it as structure. Within a decade, the tunnel becomes a man-made reef, engineering giving something back to the lake it borrowed from. Also, NASCAR currently transports entire racing operations cross-country every week. Hundreds of diesel-burning haulers on highways every weekend. A permanent facility eliminates that for at least one race per season. It's not going to save the planet, but it shifts the equation. Here's the part that changed. Bridge-tona was beautiful, but beauty doesn't survive wind shear and expansion joints. The Lake Michigan Hypertube is not beautiful. It's a concrete box buried under a Great Lake. Dank, industrial, and impossibly expensive. But every piece of technology in it has been built and proven. The physics hold up. That's what Galaxy Megabuilds is about. We don't just admire the 7 wonders. We go looking for the ones nobody put on the list yet. Share this with someone who thinks a racetrack belongs above ground. Send it to your NASCAR group chat. Let's see if we can get this in front of someone with $500 billion and a vision problem. The world recognizes 7 wonders, but there are many, many more. And that includes you. We'll see you on the next one.